Very nice to see everyone here in Perth. So yeah, I'm going to talk about dusty galaxies. And obviously, the first question many of you will have in mind is, why do we care? Do I have to care about dusty galaxies at all? Well, I want to make the case in a very general way, looking at the cosmic star formation rate history of the universe. What you see here is the contribution from obscure star formation in orange and from unobscure star formation in blue. So if you look at the peak of star formation around redshift 2, what you see is that obscure star formation wins over the unobscure one by an order of magnitude. And a lot of that star formation is actually concentrated on galaxies that are called ultraluminous infrared galaxies, which are indeed very dusty, massive galaxies in the early universe. So this is lovely. We know this quite well now, but one of the key problems that we have is that when you go to higher redshift, when you go to redshift 4, 5, and above, there's pretty much no constraints on how much obscure star formation there is. And therefore, plenty of room for, I assume this is a pointer, yes. Plenty of room for different, very different predictions. This obviously has started to change thanks to the JWST and also some new ALMA survey. So this is an example from the ALMA MORAD survey at 2 millimeters. But these are just the detections that you're getting. So these have to be seen as a lower limit for the amount of obscure star formation in the early universe. So what I'm interested in is really how are we modeling infrared in galaxy formation simulations, because it's such a critical aspect to understand how galaxies are forming and evolving. And also, more specifically, if we look at the early universe, how much room there is for dusty galaxies to exist in large numbers and for our view of the star formation rate of the universe to change significantly. So for a long time, actually, the modeling of dusty galaxies has been a pretty big challenge for galaxy formation models and simulations. And this is one of the first attempts to look at that. So what you see here is the 850, oh, I didn't want to press that red button. Oh, wait. Okay, you see here the number count, so at the 150 microns. And this was done at the time with the Galform semi-analytic model. And the point that was made by the author is that to reproduce simultaneously the abundance of optical near-infrared galaxies with that of the sub-millimeter or far infrared, you needed to invoke actually some pretty extreme forms of initial mass function variation. So what you see here in the dashed line is what the model predicted with a universal initial mass function. And in solid line, it's a pretty extreme form of a top-heavy initial mass function in starburst. So this early paper really planted the belief in the community that it was necessary to invoke some pretty extreme variations of the IMF to reproduce sub-millimeter galaxies. So we revised that in 2016 with Cedric Lakesy and the Galform crowd, looking at the same Galform model, but after many, many extensions of the model. And we basically came to the same conclusion that you needed forms of initial mass function variation that are shown here in red. Otherwise, you don't get to reproduce the right number density of these infrared galaxies. Just to show you that this is a more generic problem, I'm showing you here the same number counts with two other models, so Eagle and the Santa Cruz semi-analytic model, both of which assume a universal IMF. And the lack of these bright sub-millimeter galaxies is pretty common issue. And there was a TNG paper as well about 2 years ago looking at this, well, for Illustris and Illustris TNG, finding similar issues. So to tackle this problem, we decided to combine a set of novel ideas and tools. So our approach consists first of taking the Shark semi-analytic models, and I'm not going to say how they are built because Adam did an amazing job in doing that. I'm just going to say that it's a numerical scheme to solve for the evolution of baryons over the skeleton of dark matter only simulations. So we combine that with the Prospect SED fitting code, but in its generative mode, to model the light emission of galaxies. And probably the most novel idea here was to actually use extinction curve or sample from attenuation curves from the radiative transfer analysis of Eagle galaxies, of thousands of Eagle galaxies, sampling based on the dark surface density. So the key aspects here to remember is that in SHARC, we adopt a universal initial mass function, and we're informing the attenuation of galaxies, attenuation by dust in galaxies from radiative transfer analysis. All right, so let's look at some of the key results of this approach. So in this paper that I'm gonna present in 2019, we showed that SHARC was able to reproduce a wide variety of panchromatic information of galaxies. And I'll show you an example of that looking at number counts. So what you see here is number counts in the near UV. So there's lots of lines. You just have to worry about the thick solid line that is our preferred model, and the symbols that are the observations. There's different lines, color lines here. I just show you the contribution from different galaxy components. So I'm not gonna focus on that, but ask me if you're interested. So I'm gonna go through the electromagnetic spectrum all the way to the radio slowly. Cool, so let's go. So this is the SDSS R bands. We're going to the optical, the near infrared. We're getting to 3.6 IRAC microns. So we're getting to the point where PAHs become important. Now we're going towards the Herschel bands, so 70 microns, 100 microns, 500 microns, and the critical 850 microns. That's all the work I was presenting you just a slide before. So the fact that we were able to reproduce all these number counts across this large part of the electromagnetic spectrum is really a landmark result, because we're showing this is possible to be done with a universal initial mass function. So there's enough other systematics there that this is actually possible. And this is the first fully cosmological physical model of galaxies to show that, actually. And in 2020, we tested much more the regime of dusty galaxies, this time looking at all the ALMA bands. So what I'm gonna show you now here are number counts again in ALMA bands with the data that was available back at the time. So here you see band A, this is around 600 microns. And now you go band 7, that's around 850. Here we are looking at the black line I should have said. This is about 1 millimeter, and this is about 2 millimeters. And the agreement here is obviously not due to fine tuning, because none of this was ever used as part of the model parameterization, but really a success story of what we were doing here. And more recently in this paper by General in 2000, well, this year, they included additional bands, ALMA bands. And what you can see here now in the red line here, the SHARC, these are the new observations. And again, this looks pretty reasonable. And thanks to the work of my master student, Samuel Hansen, we've been able to now extend the predictive power of SHARC to the radio continuum. And here I'm showing you number counts at the 1.4 gigahertz and 150 megahertz, just as an example. So to my knowledge, this is the first and so far only cosmological physical model to reach this level of success in terms of this broad panchromatic emission of galaxies and compared to observations over a wide cosmic range. But I want to focus more on dusty galaxies. So let's look at this. So for dusty galaxies specifically, we tested the model much more in my 2020 model paper, sorry. And here's an example of the stack SED of submillimeter galaxies. So what you see in black, these are the observations. This is the work of Elisabetta in 2015. And what you see in red here, this is the prediction. So that would be the UV to near infrared emission of galaxies that are selected to be submillimeter bright. So the agreement here, I think it's staggering. I wasn't expecting this at all. But something that I find extremely interesting is looking here at the diversity of some of these SEDs. So this is telling us that at least within the SHARC semi-analytic model, the population of dusty galaxies of these 2 millimeter bright galaxies is quite an inhomogeneous sample. And you have some galaxies that are massive, pretty much main sequence galaxies, and others that are extreme starbursts. So it's quite a diverse sample of galaxies. So moving on, I wanted to go back to the first question I started with. That was, is there enough obscure star formation at high redshift that we think we're missing? So to answer that, I'll go back to the cosmic star formation rate density plot. That's what you see here. And the different color lines are showing you the contribution from galaxies selected at 870 microns based on their flux. So I'll just show you the main takeaway points here. So what you see in red, this could be more classic submillimeter galaxies. And what you see is that the contribution to the star formation rate density drops below 10% above redshift 4.5 to 5. But if you look at the next bin, these are still relatively massive main sequence or slightly above main sequence galaxies. They tend to dominate actually up to redshift 5.5 more or less, but the contribution drops at redshift above 8. So just to kind of take away is that if we look at dusty galaxies, they make a massive contribution to the cosmic star formation rate at redshift below 5, but very little above that. But importantly, that's not to say that dust isn't important above redshift 5. And in fact, in this paper that was led by Jordan da Silva, sitting in the room somewhere, we actually show that when you look at the UV luminosity function, you see that dust plays a very important role even out to redshift 10. And you can see that here for two very different simulations for flares and shark. So the point here is that the takeaway point is comparing these dotted lines with the solid lines. So the dotted lines are telling you what's the intrinsically emitted UV luminosity function, and the solid lines are telling you what will be observed after you consider the effects of dust. And when you can see even at redshift 10, the effect on the UV luminosity function can be 1 or 2 magnitudes at the bright end. So that's extremely important, even out to those very high redshifts. And just before finishing, I wanted to say one word about the connection between dusty galaxies and massive quiescent galaxies that are now quite popular. So this was explored in detail in this paper by Ariana Long, that's on the archive as of end of 2022. And she explored these using an empirical model to connect dusty galaxies as being progenitors of massive quiescent galaxies. The important thing for me to take away from this plot is that she also compared with shark predictions at the time and predictions from another empirical model called CITES. And what you can see here, this is the stellar density. This is for luminous infrared galaxies, or massive luminous infrared galaxies, and that's for their quiescent descendants. And I'm going to highlight here where the shark predictions are, just to draw the eye. And generally, what we're seeing is that the model predicts, at least within the current uncertainties, ballpark the right amount of stellar mass density in this type of galaxies, and also in the quiescent, massive quiescent descendants of these galaxies. So this is more to say that at least within the uncertainties and the fact that shark is reproducing some of this mass density is indicating that there's a viable evolutionary connection between these two very different populations. And just to finish up, to conclude, so first of all, I think we've done quite a lot of work to test the model across the electromagnetic spectrum and out to redshift 10. And I'm not saying the agreement is perfect. I'm saying it's actually good enough for galaxy formation theorists, I guess. This really is unprecedented. And what I like about this is that we can start to use it to make predictions. So we tested it quite significantly on the far infrared, and in terms of interesting predictions to make that I wanted to highlight is that we predict that there are not enough dusty galaxies above redshift 5 to significantly change our view of the cosmic star formation rate density. But in terms of individual galaxies, dust can still be extremely important even out to redshift 10, especially on bright star forming galaxies. And with that, I'm going to finish. Thank you.